Swayam Prabha. Digital India. Educated India.
In this lecture on design of embankments on soft soil using geosynthetics, we would be seeing the use of geocells. The geocells are a three-dimensional form of geosynthetic materials with interconnected cells filled with soil. It can be stone or even it can be a marginal material like a fly ash. The important advantage of the geocell layers at the base of the embankment are it acts as immediate working platform for the construction. Say for example, if you want to have a working platform, the soil is very soft. So, one can spread this geocell material and then start filling up soils. Actually, you can put a geotextile at the bottom, put a geocell and fill up all of those things and put a roller, then use it as a platform. Then it acts as a stiff rigid base to the foundation, promoting uniform settlements. Then it minimizes the construction time, prevents the bearing capacity failure and minimizes settlements. These are some advantages. In fact, it comes in this form like you have it can be a cellular matrix, you can just expand and then you have in these gaps a lot of soil could be compacted, and what it does is like in these cells you compact the sample and then when it expands there is a radial strain radial stresses are introduced in this system, and then they provide a confining pressure. In fact, similar to a triaxial cell, you have a sort of a confining pressure. There actually we apply the confining pressure. Here we can design these members to see that there is some rigidity or the stiffness that gets that they provide to the expanding soil mass and keep them in the confinement condition. So, because of this confinement, what we have is some cohesion gets developed because there is a confining pressure. In fact, if you look at say for example, Mohs circle envelope, like if this is you take a soil for example sand, it has a zero cohesion and then this is the failure envelope, and you just put this in the confinement with in the geocell, and then if you just apply load, it behaves as if it has a higher confinement pressure, which is something like this, and it will take even higher strength as well, like shear stress that it can take care of are higher because of the confining pressure. Like now, earlier it was this line, now this is the second line that you have. This is what happens is that under the action of the geocell, the apparent cohesion, actually the soil is essentially sand, it is like this, the Mohs circle line is like this, failure line, and once you have a cohesion introduced into this membrane material, then you have an apparent cohesion that gets introduced. So, this is an extra cohesion that you have because of this geocell. So, this extra cohesion also it is called confining pressure, So, so that is an advantage here. So, the advantage of the geocells is that they add a sort of a confining pressure. Okay. So, how do you get this confining pressure? There is some expression that is available in literature, like see the delta sigma 3 is something that you have to have, and this is an expression which is given in the literature by researchers who are trying to understand the membrane correction required for a triaxial cell. When you apply some load on the triaxial sample, even it is possible that there may be a higher shear strength because of the membrane that you have put, is it not? So, you have to correct that membrane, do that membrane correction for the cell pressure. So, in that connection they have come out with this expression, and that has been quite useful to calculate what should be the extra confining pressure because of this geocell composition. So, that is given in terms of the axial strain of the material, then the circumferential strain as well, and d naught is the initial diameter of the sample, d is the diameter of the sample at an axial strain. So, for example, if it gets expanded to some other strain level, what is that? And m is the modulus of the membrane. What is the modulus? So, tension modulus of the membrane. Once you have all of this information, it is possible for us to calculate the extra confining pressure. It is an advantage here. So, once you know the extra confining pressure, you know like what is that it is doing? It is really putting a sort of a passive resistance, right? It is not allowing, it is not active, it is a passive resistance. So, you have to use this formula Kp. So, 1 plus sin phi by 1 minus sin phi. So, you are able to get this cohesion also. So, using this apparent cohesion, one can do like that is what like one can use in slope stability calculations or bearing capacity calculations to calculate. Otherwise, the material was actually a sandy material. Now, because of the cohesion, you got higher bearing capacity. That is an advantage here. So, you can see a small example with all the geocells and all that. You can see this parking and all that. So, this is an advantage here. Okay. What it is some experimental evidences have shown that, say for example, of course, the theory is quite simple, and this because of this confinement, the failure planes are not allowed to develop. In this case, there are failure surfaces like this. Here, they are all just restricted to this area, and then they form like this. It is an advantage here. And some experiments that people have conducted, in fact, in Indian Institute of Science also a lot of experiments have been conducted on geocells, and this is an example, one of the earliest examples actually given by Professor Bathurst in Canada. And this is a saturated peat, it is an organic soil, and then they filled up to 1 meter level, and then the load is applied. It is a geocell mattress with a gravel filled in is there. And once it is loaded, you can see the difference. Like in the case of an unreinforced soil, this is that load versus displacement of the depth, but whereas in the case of the reinforced material with the geocell, you can see that there is a very big difference. Like what is the settlement or the permanent deformation is maybe, for example, if you just extend it to it 15 kilonewton per meter, it could just go up to about 350, whereas the rut depth, whereas in the other case it could be just 100. So, there is a good settlement reduction, and even if you want to take at any given rut depth or whatever, the bearing pressure improvement is quite significant. Say for example, at 100 mm rut depth, in fact, it is very useful in pavements. Rut depth is one very important characteristics. At 100 mm, you just see it is about 15 here, whereas it is about 7.5 here. You can see that it is a good difference in terms of the load carrying capacity and reduction in settlements. At any load level, there is a good difference in bearing pressure, and even settlement reductions are also possible. So, with this we have like I would like to show you some case studies on use of these geosynthetic materials. There are many actually, some I have collected from Indian Geosynthetics, International Geosynthetics Society, and the chapter of the Indian Geotechnical Society. We have an Indian chapter also for the same society, and the 3 case studies that we see in Hong Kong particularly, and other places we will see how they look like. In this, the embankment soil, the embankment was supposed to be constructed on a swamps and fish ponds, actually in soft soil clay foundations 10 meters deep, and the strength of the soil is very low, like 3 kPa is quite a low number, and they used geotextile here, like we know already about geotextiles. We use the geotextile here, and we have seen how the geotextiles reduce the preload, right, and it also avoids the replacement of soft soils. So, they have used geosynthetic band drains to increase the rate of consolidation, and they were measuring geotextile strains, settlements, pore pressures and lateral displacements. One should do this in an instrumentation project involving, particularly when you are trying to have a ground improvement technique. It is always advantageous to measure the actual quantities that may be of very importance to us in terms of calculations, theories, because we apply some theories, but then if you are able to measure the strains and settlements, pore pressures, displacements, it is going to be excellent. So, that is another one. So, they are able to see for the platform, they did like that. The other one was the another crossing where there is an extensive deposits of mud material here, like you have some other sandstone here, sands and gravels, and embankment fill is there. You have lots of desiccated crust here. They would like to use, they use a sort of a stone columns, and for that actually to transfer the load, exactly what they did was that you need to have a see, we have seen how to design stone columns, but if you are able to place a sort of a geogrid at the top like this, it can help in load transfer. In fact, load from the embankment to the pavement to the actually the stone columns could be less. So, the construction is also quite fast in this case, and this is the way that in all these materials it looks like stone columns. And there is another one that we have, there is an access road, and then it is about embankment height is about 10 meters. The embankment is founded on soft soil of 6 meters thick, and the shear strength is 10 to 25 kPa, quite a low number. And to increase, to what they did was that the solution was to install band drains to increase the rate of consolidation with a geocell matrix here as a foundation to the embankment. This is another one that say that what they are doing here. You can see that is how they placed a geocell here. Okay, like they just, it comes like this. It's a this is a geocell. The geocell consists of transverse grids with a triangular honeycomb structure formed by interlacing other sheets of uniaxial geogrid into the mesh. Okay, how it is? This is how it looks like. So, filling is being done. Filling takes place from one edge. Once the area is filled, delivery trucks can run on the surface of the geocell. Once it is completed, one can go ahead and work on it. Lateral extensions in the geocell were less than 1%, and mattress acted as a stiff foundation. It is a very good system here. Okay. There is another case study that I would like to just highlight from India. Of course, we have many case studies that in India also, and for example, this is in Gujarat, where they are trying to have a special economic zone, and the soil was very soft there in Kandla Port Trust, and there was ROB, means road over bridge, was supposed to be constructed, and so the soil was supposed to be having poor bearing capacity. So, what they did was that they used a stone column technique along with a geosynthetic raft. You have a stone columns, and then a geosynthetic raft came at the top. Actually, I was in touch with McAfee International Environmental Solutions Company in Bombay. They were able to give me this case study because I thought I should discuss this with you. In fact, this is an RE wall structure that they have made, and this is all the, this is that what we are talking about, the geocell, this geosynthetic foundation material here, and loading platform actually. Okay. This is another one, and the way that they are doing this is, you can see that they are doing the stone columns work, they are spreading that geosynthetic product. This is the completed view of this structure. Actually, even there are some cases where there are some air, the voids also are formed in the ground. I was just mentioning about one case where the possibility of voids formation in certain deposits are there, and if you do not want the loads to be transferred to that, because it is very difficult to fill up the void. The thing is, we do not know where the void starts, where it ends, and one conventional way of filling up the voids is to use a lot of cement grout, and cement grout, yes, it can be done, but at the same time, if you want to really see that there are no loads or stresses that reach that say for example void, you can put a geocell matrix at the top and see that all the load is only taken care of by the geocell matrix, the material, the whatever foundation bed. We can call it loading platform also. So, you can see that it will be much more economical than try to fill up a hole that we do not know where it starts and where it ends, right. So, there have been lot of case studies on the use of geosynthetics in India, and the science is quite simple, that I also explained to you, that particularly when you are trying to handle the embankment and soft soils, you have to calculate how much is the shear of the we have discussed about internal stability and external stability, and also like one can do that, and in the construction of loading platforms also you can use geocell foundations, and the influence of voids in the foundation medium also could be avoided, in the sense if there is some problem like that, one can do that. So, this technique has been quite useful, because in many places in soft soils there is no technique available, and this is the only technique, and people have perfected in many places in abroad and in India also. Now, I will take up the next lecture, which is on filters. This geosynthetics, as we have been discussing about reinforcement function, and now there are actually the geosynthetics are much more helpful in other applications as well. We know that the functions of the geosynthetics are the reinforcement, separation, filtration and drainage. So, when you have all of this even moisture barrier as well. So, you can use them in many other applications, particularly in the case of filtration drainage, which is so crucial in many water related projects, because we have this problem with water, that when there is water, you have high pore pressure mobilization, then drainage, if it is not there, then it is an issue. So, and then the other one is that two soils, like a poor soil, and you would like to isolate a poor soil from a good soil. So, you have to separate them, and you also need to allow only water in some places, not the soil. So, you have to call what you call filtration. So, we have in all these applications, the use of geosynthetics is phenomenal, and we can use these materials in a very significant way, and people have been using it. So, when do you need filtration? We need filtration when you want to just allow the water to go through a particular system. So, for example, the water behind a retaining wall, you would like to see that the water comes out of the weep holes properly, and see that there are no pressures on the retaining wall because of the water. So, you would like to have a clean filter, so that water only comes out, but not the soil. So, that is what and then we should retain the base soil. So, for example, whatever is the soil, backfill soil is there, if you start removing it, then it is a problem, right. So, you do not want the soil to be lost, you only want water to come out. So, that is one thing. Then you would like to avoid piping, in some cases, when in certain conditions, when water comes from bottom, there is a possibility of piping or liquefaction, we call it static liquefaction, and when the effective stress comes down to 0, the possibility of piping may come, or even there is a dislodgement of particles and all that. So, you would like to avoid piping, then you would like to allow the free flow of water. Say, for example, you would like to avoid avoid external clogging. Say, sometimes clogging also needs to be prevented, because clogging is a serious issue, and even internal clogging is also possible. Say, for example, what happens, you have some soil, base soil what you call, and then at the top you have a filter. So, water goes from here, then what happens is that the filter should be able to only allow the water, right, and then it should also not lead to, that filter should not get clogged. The clogging is two reasons we have. One is external clogging at the periphery, and the internal clogging also, because of many other means like biological and other means, and both should not happen. And the thing is that if the filter does not work for properly for even for a short term, then it is a serious problem. So, you must be able to design the filters in such a way that they take care of the environmental stresses, like wetting and drying. Even the water flow is cyclical, the water comes up and goes, and when you have this sort of situations, the water flows are cyclical, and the filters should work properly. Otherwise, you will have lot of serious issues, and these functions can be provided by natural aggregates, like you can just use sand alone or filter paper or anything like so for example, fly ash and all that, and geotextiles are also useful. So, we will see what is the difference between aggregates and geosynthetics. Like I just was mentioning about the clogging, I think I must just mention about it. The internal clogging is because of the fine particles of the soils to be filtered, bacterial activities, then some sometimes in some places abroad, they when you want to remove this ice from the airfield pavements, they use de-icing salts. So, they lead to some difficulties in filtration, then ice lens formation, other things. So, anyhow, most importantly we need to avoid this, and we should understand what is the difference between conventional filters which we use like sand and all that, and what is the geosynthetic filters. First thing is the thickness. Thickness can be, as normally you have to provide some thickness like 100 mm to 150 mm, where you need to get a actually gradient you should get, but you do not need to have that much thickness here. Thickness is quite less, it can be just 3 centimeters, 30 mm, which is quite simple, whereas this is 15 centimeters, this much, and it is at least 5 times less. Then these materials are, porosity of these materials will be about 25 to 40%, whereas the porosity in this case is much higher. You are able to make the channels properly, you do not allow the water to go. So, porosity can be higher actually. Then the capillary rise is another important property. In some materials, the capillary rise is nothing but because of the capillary forces, the water will rise because of this rise of water column is known as capillary rise, and this can be 500 mm, and in a clay soil or in some materials it is not very good, like if the capillary rise is going to be higher, it wets the surface, which may not be necessary. It creates pockets of weak localized weak pockets. Then here the capillary rise is less. Then aggregates, the compressibility is less, whereas compressibility is little more in the case of geotextile, because geotextile is actually a compressible material, right. Then transmissivity under confining stress, yes, it does not depend so much on the pressure, but it varies as a function of pressure. Then what about uniformity? Uniformity of the aggregate materials. Actually, it is not easy to really get a good gradation and control on the gradation, because you try to use whatever material you get from the borrow pit materials. Then you try to check if it can satisfy as a filter. The second thing is that the factory control, the geosynthetic materials are factory controlled materials, and the thickness and area, they are all mass per unit area, the another property, they are all constant, or they have some fixed numbers, whereas this is somewhat different. Then durability, yes, aggregates are excellent, and of course geosynthetic materials, they have some influence of ultraviolet rays, that is one problem. Installation must not be contaminated by surrounding soil, and compaction is required, whereas installation is easy because it is quite convenient to put a geotextile, and also that you can, even if the soil is contaminated, there is no problem actually, okay. Like the soil can be in touch with the contaminated soil can be in touch with the filter. Risk of damage, of course, aggregates, there is no problem at all, whereas in geosynthetics it is subjected to puncture and tearing, so one should be careful. So, what is this clogging? Clogging is something very important we should understand, particularly in the case of filters, that the voids are getting filled up by the solid matter, to the point that there is a passage of the water is compromised. So, there is a decrease in hydraulic conductivity. Then internal clogging is also possible by mineral particles, by precipitation and chemical deposition in the voids by water containing iron de-icing salts, biological growth, incrustation in aerobic conditions. This is in a way depicts the filter base filter interaction. See, external clogging, this is a geotextile material, this is a TGT is the thickness of the geotextile, and if there is some deposition here, the geotextiles can lead to clogging, that is external, and internally also it is possible that it can clog, like this with some biological depositions and all that. Clogging of particles is also possible here. So, these things one should understand, even this is actually also possible in the natural aggregates, but one thing one should remember is that the paths are continuous. In the case of geotextile, it is much more porous compared to the natural aggregates. Where do you use them? Applications are too many. Whenever there is a water flow, and if you want to make it properly flowing, we should use drainage. Having good drainage functions are important. So, beneath pavement bases and base courses, retaining walls and bridge abutments, drain and well pipes, slope stabilization, earth dams and levees, many. Like erosion control, like it protects the runoff collection, slope protection along stream banks, score protection around structures, construction facilities across and adjacent to water bodies, culverts, drop inlets, artificial stream channels, etc. So, this is a typical example, like you have a pavement shoulder, then soil subgrade, and the geotextile is put like this. You can even, this is a pipe here. So, this is how it is done. And in the case of retaining wall, this is the way it is done. Earlier you had some 30 centimeters or 50 centimeters gravel here, okay, gravel, and then start compacting it. That is how we do it. So, then you have it simply, you have a geotextile here, then it has a drainage here, that is it. Then erosion protection, like see, you have a geotextile here. What happens? We do stone pitching in the, we are used to this pitching of stones, keeping like this, but still they do not last, because the possibility, what happens is that this pressure, the water, the phreatic line comes here and then it reaches here. The possibility is that what happens, because there is always soil and aggregate mixing up, there is always pockets of low settlements and other things, and finally it leads to lot of disfigurement of the whole area. But if you have a geotextile like this, then it is only the water that is allowed, and the soil that is there as working as a slope stands there. Okay. So, that is one important point. And so, in the case of dams, like one can put a geotextile here, okay, one can put a geotextile here. And consolidation, vertical consolidation drains, we have already seen that you have a prefabricated vertical drains in which the central portion is it has a drainage channels. Then the cover, it is called the cover acts as a filter, because it only allows the water, and then the water reaches at the top and bottom, and it gets pumped out. Then there is another one, that in some places what you call one can have sediment tanks. If you have a material like this, it is easy to clean them also, and then the possibility is that sediments get deposited like this, and then one can effectively, this also acts in this cases. So, there are many applications here for particularly filtration drainage. There are so many applications that one can think of, and actually the maximum use is in this area, because as I said, wherever there is a water problem, water plus soil related problem, it is better to isolate them, and problem is reduced. There is another important point that we should understand, there are two types of flows, one is a static and the other one is dynamic. What is a dynamic flow? The dynamic flow is nothing but it is cyclic, pulsating, like in the case of or high forces, whatever it can be, and in some cases it is static and unidirectional. So, where is it in dynamic and pulsating? Actually, in erosion protection systems, where the water comes and continuously impinge on the shore protection systems, it is a dynamic. Road drainage, it is a combination of traffic, and the thing is, the moment there is a load on the traffic, the water goes out, and if water goes, there is always that cyclical response that is there at the fundamental level, and the conditions are supposed to be more severe here. Like why this distinction is important is that we should understand what is the force acting, how do you handle the filter design. Okay. Then static and unidirectional. In the case of wall drains, in the case of silt fences, in the case of vertical consolidation drains and earth dams and core, there is all no problem at all. They are all unidirectional. Okay. And one should also understand the nature of critical nature of the these problems. Particularly, one should design the systems in because unless you understand the criticality of the the projects, say for example irrigation projects, if you do not understand the criticality of the projects, then it is very serious. And so there is a need to understand to what extent it is important. Say for example here, critical nature of the project, risk of life and structural damage due to drain failure. Say for example, the drainage is not good and then there is a pore pressure development and all that things are there, then the requirements are going to be very high. Criticality is very important, right. Repair cost versus the installation cost of the drains. So one should be able to understand what is the difference, how much the repair could cost and how much is the cost of reinstallation. Some of these things one should be able to understand. So that could be okay. If it is not much, it is equal or less, then less critical. Then evidence of the drain clogging before potential catastrophic failure. See, in some, if you have information about the possibility of drain clogging, then it is much more easy to handle and it is much less critical. Otherwise, if it happens after the damage and all, it is going to be serious. Okay. Then what are the other issues that we have? One is that if the type of soil is, it also is a function of the type of soil. If the soil is gap graded, okay, or pipeable, pipeable means that it can easily come out, or dispersible. If the material, if it is well graded, then the problems with filtration are less, like because what happens, the pores are all the distribution of particles is so well presented in that particular the material that there is no problem of pore pressure mobilization and all that. But if it is a gap graded material, the problem is that water gets accumulated and there is a pressure and then there is a possibility of damage. So, soil to be drained, so this is a severe condition, this is less severe. And then hydraulic gradient, if it is going to be high, it is going to be definitely the condition is severe, but if the hydraulic gradient is low, then there is no problem. Flow conditions, yes, if it is dynamic and cyclic, one should understand that properly. And then steady state is another issue that like it is not serious, like if it is smoothly flowing, then there is no problem. But in some other case where there is lot of erosion and then there are lot of waves and all that, if the possibility of damage is going to be high, you have to understand that it is going to be severe. So, the objective here is that why are you discussing this is that essentially the previous case was also we should be able to understand the critical nature of the project, to what extent they are going to be very important. You assign that yes, it is critical or less critical depending on the nature of the project as well as type of soil, okay, severity of the conditions. You may remember that with all these problems associated with the importance of the design that you have, the design criteria is very empirical. what we do is that if you want to retain the soil, say for example, you do not allow the soil to go out, we have from the grain set distributions, you take a D15 of the soil from the filter, D85, the grain set distributions, both of them you have, and then if you say D15 by D85 of the soil, if you find the ratios to be less than 4 to 5, soil is retained. That is the criteria that given by Terzaghi. Then permeability criteria, D15 of the filter should be much higher than the D15 of the soil, like at least 4 to 5 times. So, that is what we say. These are the two filter criteria that we say that we expect that it is going to be satisfactory, which is not really not easy to say. Why? Because just if you follow some of this criteria like that, how are you sure about time dependency, and how do you expect the filters to work for 5 years? Where is the check here? There is no check. Okay. But then people have been living with this, and then of course, there are a lot of theoretical work, but this have been more or less practiced to a maximum extent. So, now we know that geotextile performs better for the simple reason that it can create a cleanly it removes the water and thickness is less. We saw the differences between a geotextile filter and a regular filter like a aggregate filter. The difference is good, and if if you are putting the geotextile, you should also design it properly. One is retention criteria and permeability criteria and anti-clogging. So, people have thought about, okay, Terzaghi's criteria of just soil retention permeability may not be sufficient. We should have some more information, because when you are putting a geotextile, it should work properly. That was the question. So, the people looked at it, okay, if I am putting a geotextile, it should not get clogged. So, anti-clogging criteria was put. Then there is a serviceability criteria, like it should be able to work for some time. If it does not work, there is no use. And then durability criteria is also specified. So, this is another the criteria that they have introduced, because whatever you do should be durable. Like if it lasts for 6 months, if you do a design, filter design, and you do not know how it works, or if it only lasts. See, the only problem is that if the filter fails, you will immediately see the result, like water logging in the area, all some of these things, right. So, how do you get some more information from this is something that in fact there was one Professor Giraud who did extensive work on filter criteria. There is a lot of very interesting work, and he came out with a simple design procedure that we will discuss. And what are the design parameters? He looked at the thing is grain set distribution is one thing. So, coefficient of uniformity is one thing which is we normally use. Then he also defined a term called coefficient of linear coefficient of uniformity, then coefficient of curvature. These are some terms that that are useful, and he prepared. Say he realized that apart from the particle size distribution, you can also have some idea about Adderberg limits, dispersion potential, because dispersion potential is another important thing, and the density of the soil is also important. Some loose soils, they have a tendency for they become very loose, they are very loose, and the water may, if there is a water availability, soil and water both come out. So, density is very important. So, density, all these things are all very important, and he prepared some design charts which is very interesting. And he also identified the hydraulic gradients, because the hydraulic gradient in each problem application is different, and one should use gradients properly. Otherwise, the you can't assume the same type of hydraulic gradient everywhere. The behavior, say for example, in the case of a dam, it could be different. In the case of a small trench, it could be different. So, he identified typical hydraulic gradients. Say for example, standard dewatering trench, it is about 1, vertical wall drain about 1.5, pavement drain it is 1, and landfills it is about 1.5, dams 10, inland, so liquid impoundments 10. He is able to identify, say for example, if you just identify the filter to be very effective, you say that the filter has to be working there, then what is the pressure that is acting on it, and what is the hydraulic head it is coming on that. You should be able to understand. Like one can do all of these things from flow nets, right. We are familiar with flow net construction, and one can simply know the steady state conditions of the water flow, and if you know the structure, whether it is a pavement adjacent or a dam, and you will be able to know where is that piping chances of piping are there, what are the chances of hydraulic gradient being low or high, one can calculate and then come out with some understanding. Otherwise, it is very difficult to just based on the soil retention criteria and permeability criteria alone, it could be very difficult. Okay. So, the other important thing that he made was that soil conditions, if it is a loose soil like unconsolidated material or a uncompacted material, the relative density is about the confining pressure is about 50 kPa, the load is not much. So, the relative density is in the less than 35%, and if it is high confining pressure, he is the relative density in the range of 35 to 50 actually. So, it is then consolidated residual deposits 35 to 65 and relative density is high. Okay. So, some of these numbers he has given, and so he has been able to identify the pressure or the hydraulic gradients, the type of soil influence, the type of pressure influence and all that, and he proposed a retention criteria using geotextile. What is that retention means? The material should only allow the water to go out and soil should stay back there. So, the apparent opening size of the geotextile should be less, because it should be less, otherwise the particle will come out, right. So, it is some ratio of the D size of the soil, there is some factor B here. So, the effective opening size in geotextile for which E is a openings that are smaller than this O90 we call it. Okay. We call it O90 sometimes, and less than or equal to B, and it could be some number, it can be 1 also, like B is a coefficient. Normally what we say is that like the D soil is a representative soil particle size, usually the medium to larger fractions, like you take larger size particles. In fact, we also defined in the regular criteria, and it should not allow the soil to go out. So, it should be so small, and you also compare with a bigger size here. So, some ratio it should be 3 or 4 or whatever we said. Okay. So, the same this apparent opening size, how do you get it? There is a test here. Okay. There is which is called O90 size, and apparent opening size actually we discussed earlier in the hydraulic properties of geotextiles. It is just obtained by a simple test in which you can have a series of glass beads, say for example, the glass beads can be of different standard sizes, and it can be you place that soil particles geotextile sample. You can see there are 2 samples here. There is a water flow, feeding water flow, soil particles, then geotextile sample and collecting trough. So, like you have that soil particles, you say 0.1 size, or you make some material here only with uniform size actually 0.1, and then you have a geotextile, allow the water to go out, and water cleanly goes out. In some cases where 90% of that of the whole water comes out, that size corresponds to O90 size, apparent opening size. One can characterize the geotextile based on the apparent opening size, right. So, once you have that, there is this is a test that we should do, and there is a chart that is given by the Professor Giraud. There is a simple explanation here. Of course, it is not very clear, but at the same time I suggest you to see the textbooks that are available on this topic, but because it is very difficult to, it is a big chart and it is very easy to, it is comprehensive chart. This chart needs, say for example, there is a tank bund. You do not want water to see that the tank bund should be stable, and it should not be the soil tank bund should not get erosion type of failure, and all that is our question. What you do is that now you want to do a filter stone pitching or a filter pitching for it, and you want to come out with a simple design for filter. That is our objective. So, what is the procedure? You take soil samples from the area, then find out its clay size, percent clay, more than 20%, less than, there you have a clay. What is the clay content? Once you know the clay content, you can use that appropriately. So, for example, in this chart what I want to say is that if the clay content is more, then the possible, like more than 20%, the possibility is that you should check if the clay is a dispersive type of clay. You know, clay, there are some clays that I saw that the moment you put in water, it just starts coming out. So, for example, if you are trying to put a nice, you want a nice water body there, and then you want a nice slope, and the water should be nice and the slope also should be nice, but that is what you want, but you do not want the slopes to be collapsing out of erosion. So, you want to really check if this clay that you have, say for example, the moment the soil testing results show that it is more than 20% clay, you have to see whether it is dispersive soil or non-dispersive soil. So, there is a test for it which is called we have some provision there, what is called double hydrometer test is there, and based on the test you get some result, and whether if it is less than or equal to 0.5, then it says that you have to provide an upper and opening size of less than 0.21 mm. Like geotextile, the size will be so fine that it gives a size of 0.21 here, and if it is somewhat dispersive, then he says that you have to put a cushion of 3 to 6 inches of fine sand between the soil and geotextile. If the material is so dispersive and if it has a tendency, you need to put a cushion and then put a geotextile, otherwise even geotextile may not be effective. Then if the material is less than 20% clay and more than 10% fines, so there is some more criteria here. Is the soil plastic, if they or non-plastic? If it is plastic and like Pi more than 5, there is again it goes back here, and if the plastic, it is not plastic, then again it comes back here, like we come to this chart. And if the sand material or whatever, no, it has less than 10% fines, and this is, then it goes to this material, and if it is more than 10%, more than 90% gravel, sometimes it is just a gravelly deposit in situ, then he suggests to provide like case like this. So, put some sort of, if it is fully gravel, then you have to put some sort of sand cushion on the geotextile, you can't just, so that is what he says. So, and then if it is many of the materials fall into this category, because it will be less than 10% fines and less than 90% gravel, and we should also see that, we should understand that there is a difference in terms of application. Do you want water to flow, like application should favor permeability, or you want soil to, you have to choose. The thing is, there are two things here. One is that the flow of water, soil retention is something, so from the point of soil retention you need small pores, right, but in terms of the permeability criteria you want big pores. You understand, the same, they both are contradictory requirements. It's very, so the thing is that it's a very like based on grain set distribution only you want to get everything again. So, it's very tricky contradictory requirements, and what we do is that in some cases we should decide you want application just retention alone, or more retention, or more permeability. So, in some cases where you want more retention, there is a system that we have where if it is a stable soil based on Cc and Cu and all that, one can get, and then if the Cu dash, we have widely graded material, and you can find out its say for example, if the application favors retention, one can, and then it is a stable soil, then you have a system like this, Cu dash also you can find out, and if you know the relative density of the material also, then you can find out the O90. Actually, the whole exercise here is to calculate O90 size of the material. What is this? Is actually a retention criteria, soil retention criteria for steady state conditions. Okay, there are two types of conditions. One is a steady state condition, the other one is a dynamic condition. Okay, in both the cases, it should be possible for us to find out what is a steady state condition, what is a dynamic condition. Okay, so in the steady state conditions, where is a single flow, this chart from soil suspension criteria, it gives the apparent opening size. Okay, you can see here O95 should be less than 0.21. Okay, so the other thing that I was just mentioning, coefficient of uniformity linear one, it's square root of d100 by d0, there is another term, and then Cc we know the definition, d30 whole square by d16 to d10. All these terms are important in using the fix in soil suspension criteria, because you want a very thin pore, thin size to see that the water only, the soil is retained, not the water. Okay. So, this is for the dynamic conditions. You can see that it takes care of you have a soil testing results, and then you have some gradation characteristics. What is it severe wave attack, or is it a mild wave attack, and then is it a plastic soil, is it a non-plastic soil, is it a dispersive soil? All that criteria is actually addressed in this, and once we have this, then one can choose a proper size of the geotextile. Okay, once you know the size of the geotextile, of course, from suspension criteria, you also should see what about permeability criteria. The objective here is that the permeability of the geotextile should be more than the permeability of the soil, right. The water, it should be able to allow the water to go out, and then that is a function of the hydraulic gradient IS. So, if it is more than 1. Then even federal highway code, like of course in India we do not have rigorous codes on these lines, but normally we follow federal highway as well. So, here again K geotextile should be more than or equal to like a factor of safety 3 or 4 or whatever of the soil. And then we also have what is called permittivity. As I just mentioned, the permittivity is another number, like as I said, thickness is an important parameter in geotextile. So, K by T, thickness K is nothing but centimeter per second divided by centimeter. So, you will get, we call that particular thing as permittivity, which is we denote by xi, because if you want to compare different types of geotextiles of different thicknesses, how do you compare? I must only have some dimensional way of, non-dimensional way of doing it, which is in terms of this, because that is important, whereas in other cases like stones, we do not have that type of criteria. So, this permittivity criteria is another important, and permittivity allowable should be more than required, that is one thing. And for less critical conditions, the K geotextile is more than or equal to K soil, it is fine, but for severe condition the factor of safety should be good. And minimum permittivity conditions, as I just mentioned, it is centimeter second by centimeter thickness. So, it comes in the units of second minus, and it can be 0.1 to 1. So, these are all some minimum criteria that they have given, and if you just see any of the manufacturing product literature of the geotextiles, they will all have this information. Actually, this is another important relationship. This is called typical hydraulic conductivity values. In fact, if you know the D10 of the particles, you know how to get K value. So, that sort of relationship is given by this is instead of D10, this is D15 size, and if you know the D15 size of a particular material, you can find out its permeability, and if you know the confining pressure also, in the code, in the Gerard method they have given this, and say for example, if you know the D10 of the soil and then it is subject to high confining pressure, the permeability is some number here, and if it is subjected to low confining pressure, it is little higher. So, like that one can calculate, because it is very difficult to do permeability tests all the time, right, in the field and all that. So, these are just in the absence of any test, one can do that. So, anti-clogging criteria is something that is another important thing. So, we do not want the material to be clogging. In fact, in some cases we can repair, but in landfills, in the landfills, if the things get clogged, what happens? Leachate gets generated, leachate gets accumulated actually, there is no way to remove the leachate. So, what people will have is that in landfills, they have an automatic flushing systems. If you go to a landfill, they will have an automatic flushing systems, in which the moment they know that the hydraulic head has increased, they will have monitoring also how much of leachate is there in this particular locality, one can monitor actually. They will put all the pipes, instrumentation is heavily done in landfills, and once there is a particular problem in a particular area, then it gets showed up as gas and leachate generation. Both gas and leachate generation, if they are very high, then we know that there is a problem, right. So, you have to understand that leachate particularly, there could be some problem, because it brings lot of load on everything. So, the number one, it increases the chance of contamination of groundwater, it increases the load on the leachate collection pipes, everything. So, the moment you have that, so people will have this automatic flushing systems, and anti-clogging should not occur. So, anti-clogging criteria is important, particularly in landfills. There will be lot of bio systems, biota. So, they have a possibility of creating this clogging. So, how do you do that? Avoid clogging. Best is to increase the size of the pores. So, if it is a non-woven material, like you discussed about two materials, one is non-woven and woven. For non-wovens, we see that the porosity of the geotextile should be it should be at least 30%. The second thing is, if it is a woven, the percent opening size should be more than 4%, and the porosity of the non-geotextile is given by n into this 1 minus mu into thickness of that, mass per unit area into thickness and the percent, everything is coming here. So, once you have this, that is fine. Then there is some more, you are putting a geotextile, we should also see that it should stand the installation conditions. The geotextile should not get punctured and all that quite easily. So, we have what is called installation conditions, which needs some minimum strength. We discussed about grab strength. There are so many parameters that we should have, like so all that was is presented in terms of so depending on the contact stresses, like is it moderate or severe, or all that. So, it gives, say for example, grab strength of 90 pounds is okay, and elongation 15%, then seam strength 80%, puncture strength 40 lb, they are all in pounds actually. This is 80, so 90, 80, 40, these are all in pound. They are all representative test, you should get all these numbers are given. So, normally the geosynthetic companies really see that these specifications are met. The other one is that you should just see that the durability criteria, you are trying to use geotextiles, and they should not have wrinkles and all these problems, ultraviolet resistance and all, and chemical resistance also should be able to see that. So, exposure to sunlight extensively should be prevented, and they have antioxidants in that material and all that, and they should also be resistant to chemicals. So, what I would like to say is that these 5 criteria are very important. One is soil suspension criteria, permeability criteria, anti-clogging criteria, then survivability criteria and durability criteria. Once all these criteria are satisfied, then apart from then it is fine. In a conventional geotextile, what are you doing? You have only 2 criteria that we are doing. One is just soil suspension criteria, the other one is permeability criteria, using those D60, D10 sizes, that is all. There is no other design method, but Giroud has he has looked into more detailedly and looked at all these factors and then come out with a design method which is quite reasonably well established. With this I will conclude, and we will see some more examples on this filter design. Thank you.